Okay, so welcome back to class this morning. The plan for today is to finish up the last little bit of section 3.2, slope of a line, and move on to 3.3, finding the equation of a line. The quote or the idea of the day today is to make strategic use of the learning curve. So kind of two ideas for today, pretty quick ideas. There's the so-called learning curve. It kind of looks like this. And you can kind of interpret this in a couple different ways. But one way is something like time versus expertise, like time spent in a subject versus how much expertise or knowledge or whatever it may be that you gain in that subject. And the point is that if you spend a little bit of time, you get a lot of yield out of that. But if you spend an enormous amount of time on the margin, the yield is much smaller. So, for instance, to become like the top 10 amongst the top 10 experts in the world on some subject takes an enormous amount of time to gather that much expertise because you're all the way out here on the learning curve. And you almost need to devote kind of all of your time and effort and energy to that one topic to reach that level. But can you reach a level that's, say, better than the average person or in maybe the top 25% or something? That's much more achievable. And you could actually reach such a level in a much wider variety of subjects than, with the same amount of time than you would spend in one subject if you were trying to actually absolutely maximize that one subject. So, um, a lot of the times in the job market or in our lives or whatever it may be, you know, a lot of times it's better to have kind of little pots of knowledge where you can go fairly deep, maybe not as deep as some of the best people in the world, uh, but also to have that breadth, right? So having a little bit of uh, having some breadth as well as a little bit of depth, kind of across a broad range of areas, and then being able to go pretty deep into a couple areas um, is usually a pretty good kind of, you know, roughly speaking, like career strategy or something like that. So just one thing to kind of think about, when you're choosing your coursework, do you want to choose it all in this one narrow area, or do you want to maybe choose a couple electives that branch you out a little bit, give you a little bit more breadth? Um, will the yield for something like that be higher in your career? And it depends a little bit on what career you're going into and what other field you're looking at studying and so on. So there's a lot of caveats to all of this. And then this is kind of related to an idea. This is kind of an idea of mine, so I don't know, take it with a huge grain of salt, but I think of there being kind of quadrants of knowledge related to two axes. One is how quickly does the knowledge that I put in effort to gain, how quickly does that knowledge lose value? So is it fairly static in the sense that if I learn something, that knowledge basically is still useful, a week, a month, a year, 10 years from now? Or is it very dynamic? If I learn something today, a year from now, it's obsolete. And then on the other hand, we have what you might call, say, trivial knowledge. So quite literally trivia. So things that are kind of isolated facts that don't really relate too much to other ideas or facts. They're kind of just isolated pockets of information versus something that I call more foundational. In other words, if I learn this fact that's easily relatable to lots of other things that I know, that maybe gives me different perspectives on things that I already knew, that maybe makes it easier for me to recall things that I already knew, and it maybe allows me to branch off of that newly acquired fact and learn something else now that I know that. So, I mean, math is very much this way that we learn a certain thing. Like last time we learned, well, what is a line? What do we mean by slope and so on? And then this class, we're going to look at finding the equation of a line. So that obviously builds off of what is the slope of a line, what is a line in general, and so on. And so I think that, the more time you spend in the kind of static foundational quadrant, the more effort you put in here, in some sense, the more the rewards, right? Because you learn a piece of information, it doesn't, its usefulness doesn't decay very quickly over time, and you can build off of that information and learn new stuff as well. And I would generally kind of stay away from here, this kind of trivial where I learn a piece of information and it's kind of just separated from all the other pieces that I know. So I just know all these little pockets of information and dynamic. I put in the effort to learn this information. I spend an hour studying something or learning something or reading something. And then, 2 weeks or a month later, it's obsolete. So now that's not to say that you should never know any trivial dynamic information. I mean, some careers are essentially based on that, like IT support, right? I mean, you're always learning what's okay, they came out with a new edition of Microsoft Office. All right, what are all of the changes? And that in the 3 years, that's going to be, at least some of that information is going to be obsolete. And knowing that the file menu moved from here to here or something like that, that's not really a piece of information that's attached to anything else. But if that's the career you choose, just know that a lot of your time and effort is going to be spent kind of you know doing what kind of feels like relearning what you've already learned. And if that's cool with you, if you find that, a lot of people find that interesting, they like to keep up with all those changes. Taxes kind of the same way. Every year there's a whole bunch of new, changes to the tax code and all that. And some people just really like that challenge of keeping up to date with everything. But just know that, that's the type of field you're getting into, as opposed to something like, math or physics or something where it's a lot of static foundational knowledge. When you learn something, that's kind of the way that it is basically for the rest of your career. So some people like that structure, some people don't like that structure as much. Um, but obviously being a math guy, I tend to favor kind of sticking to this quadrant and learning things that don't really change too much over time and that I can build off of. That's not to say that that's the best quadrant, um, but at least have a think about which quadrant you like best or you favor, um, and how that will relate to your career. Okay. Any questions on anything? For anything from last time or on the homework, anything like that? All right, so we're going to finish up section 3.2, slope of a line, and then move on to 3.3. I feel like I'm coming down with a bit of a head cold today, so I'm a little sniffly and my throat's a little scratchy. So, but I think we should be able to make it through an hour, no problem. Okay, so use the slope and intercept of the following line to draw its graph. So remember that the slope was the rise over the run, or it was the difference in two y values over the difference in over the difference in two x values. So if we have 2 points on the line, x1 comma y1 and x2 comma y2, this is how we get the slope. And the intercept is the y-intercept is when x is 0, what is the y value? Okay, so for this equation, we have 2x plus 5y equals 8. We can find the y-intercept by setting x equal to 0. And this tells me that y is 8 over 5, or we could write that, I suppose, as 1.6. So my y-intercept is the point 0 comma 8/5 or 0 comma 1.6, whatever way you like to write it. And then for the slope, I need 2 points on the line. I already have one point, the y-intercept, but it's kind of a messy point. It's a fraction, so, or one of its components has a fraction. So I don't think I'm going to use that one in the calculation of my slope. I don't really want fractions inside of other fractions. That's going to get messy. If I really had to, I suppose I could make that happen, but I don't need to here. I noticed that if I pick y equals 0, I get 2x equals 8 or x equals 4. So one point that I have is x equals 4, y equals 0. And this we would call the x-intercept. It's where the line crosses the x-axis. It's when the y value is 0. Now, I kind of see that if I put a whole number in for x, like 1 or 2 or 3, I'm going to have like even number plus 5 times something equals even number. I think this is going to make my y kind of annoying to deal with. But if I put in say something like y equals 2, forcing this 5y to be an even number. So if I pick, say, y equals 2, that forces 5y, 5 times 2 to be 10. And then I can say 2x plus 10 equals 8. That means x has to be 1. Right? So I can kind of work backwards and make sure I don't get a fraction that way. So another point on the line is 1 comma 2. I can find my slope then. And let's see. I guess either way that I set up my 0.1 versus 0.2, I'm going to end up with a negative number either on the numerator or the denominator, so it doesn't much matter. I'll call this 0.1 and this 0.2. So for my slope, I have y2 minus y1, or 2 minus 0, divided by x2 minus x1, 1 minus 4. Or this is 2 over negative 3, which is the same as negative 2 over 3. And that's my slope. So sometimes we get fractions out, right? Sometimes it's not the nicest, uh, not the nicest result in the world, but we can still deal with this. So I have 0 comma 8/5 or 0 comma 1.6. So that goes somewhere around there. And then I have a slope of negative 2/3. So what does this tell me? This is my rise over my run. This tells me every 3 units I go to the right, I go down 2 units. So this point here, let's call it roughly 1.5. If I go 3 units to the right, I want to go down 2 units. That's going to be somewhere down here at like negative 0.5-ish, right? Well, maybe negative 0.4, but this will get us close enough. So if I go over 3 units, I want to go down 2. And using my intercept and my slope, I get this line. Okay, any questions so far? Okay. So moving on then, the next topic we're going to start looking at is kind of forms for equations of a line. So in this line up here, we would call this probably something like standard form. So let's even just write that down. Something like maybe standard form, or something like general form, might look something like ax plus by equals c, where a, b, and c are some real numbers. Now, there are some situations where this is a really nice way to have our linear equation written. Say, in particular, if we're solving like a system of equations, it's often really nice to write our equations this way, so that kind of all the x's line up and all the y's line up and the constants are separated from them. That tends to set us up pretty nicely for solving a linear equation. As far as graphing and understanding slope and so on, though, there's two other forms that are a lot more helpful in these contexts. So the first of these is the slope-intercept form, which you've probably heard of before. The slope-intercept form for the equation of a line is y equals mx plus b. So here m is the slope, and 0 comma b is the y-intercept. What's the benefit of putting equations into specific forms? Well, I know that when my equation looks like this, y equals mx plus b, I can just look at the equation and figure out what the slope is, what the y-intercept is. So if I had, y equals 3x plus 1, I know right away without having to pick points or plug in values or anything, I know that the slope is 3. And I know that the y-intercept is 0 comma 1. I don't need to plug in points. I don't need to do rise over run, any of that. I just know it by looking at this form. So when I get the y all by itself, when I solve the linear equation for y in terms of everything else, and then I combine like terms, get all the x's together, I have a single x term, and then get all the constants together, I have a single constant term. I've collected all of my terms in such a way that I can just identify the slope and the y-intercept just by looking at the equation. Or if I had something like, 3x plus 2y equals 1, I can I can solve this equation for y. Maybe I subtract 3x over, and then I divide everything by 2. And again, with this 3x plus 2y equals 1, if I wanted to find the y-intercept, I'd have to plug in x equals 0 and figure out what the y coordinate, what the y component of that coordinate is. If I wanted the slope, I would have to pick another point or maybe two other points and do my slope formula. But by solving for y and putting things in the slope intercept form, I immediately see that I have the slope here of -3/2, and I have the b, the y coordinate of the y-intercept at 1/2. So my slope is -3/2, and my y-intercept 0 comma 1/2. As a side note, we have a couple of kind of special cases. We have the idea of a horizontal line and a vertical line. So if I have a horizontal line going through, say, a y-intercept of 0 comma b, I actually kind of know that its slope is 0, right? If I go 1 unit to the right, I go 0 units up or down. So this actually doesn't break the slope-intercept form. It just looks a little bit different. When I plug in m equals 0, a horizontal line has slope 0, I just get y equals b. So the equation of this line is just simply y equals b. Another way to interpret this or to think about what this means is if I just look at my two-dimensional plane, I have lots of points, right? I have point 1 comma 1 or negative 2 comma 5 or tons of different points. If I impose a restriction, if I say I only want the points, the XY coordinates that satisfy, maybe say this equation here, y equals 3x plus 1, that selects a subset of those points. The ones where the relationship between the x and y coordinates respects this equation. Lots of the points that we started with across the whole 2D plane will not follow that relationship, but some of them will. If we think of that here, if I say the line y equals b, I mean, this hardly even seems like it should be a line, but what are we really saying? I'm saying I'm imposing a condition on the points that I'm allowing to be considered. Initially, I was kind of considering the whole two-dimensional plane, but now I'm only considering points to look like x comma b. I can pick x however I want, but y always has to be b. So allowable points would be, say, like 0 comma b or 1 comma b or negative 10 comma b. These would be acceptable points, but not something like 0 comma b minus 1 or 3 comma b plus 1, something like that. So if I say y equals b, really what I'm saying is I'm considering the set of points where the y coordinate is just the number b and the x coordinate can vary however it likes. Right? So like 1 comma b or 0 comma b or negative 10 comma b, all points on the horizontal line. All right, so for horizontal lines, it's not too bad because we see that with the slope being 0, we just plug that slope into our slope-intercept form and we get y equals b. Again, it looks a little bit different at first glance to say that something like y equals b represents a line in two-dimensional space. We would usually think of that as just being kind of the solution to a one-dimensional equation, but we can think of it as a line in two-dimensional space. So now what if we have a vertical line? A vertical line is one with undefined slope where like it's straight up and down. So if I even ask the question, if I move to the right 1 unit, how far do I move up or down? That doesn't even make much sense because my line is straight up and down. I can't really move to the left or right. But if we think back to this example by analogy, if I have a vertical line, and if this goes through, say, the point a comma 0, well, if I had, a y coordinate of 1, this would be the point, say, a comma 1 on the line, or a y coordinate of negative 2, this would be the point a comma negative 2. Well, really, I see that, again, I started off with kind of being able to consider any point in the 2D plane, and I restricted myself to this vertical line. All of the points in this vertical line actually have the same x value. We'll call it x equals a. So what's the restriction that I'm imposing here? It's really just the restriction x equals a. So that's the restriction that I'm giving here. Now, a vertical line has undefined slope or maybe something along the lines of something like infinite slope. That really kind of doesn't work with the slope-intercept form, right? So, the vertical line kind of does break the slope-intercept form. It doesn't just look a bit different like y equals b does, where we're just kind of missing out on one of the terms because the m zeroed out that mx term. Here, the vertical line really kind of does break the slope-intercept form, so we need to have a special case, x equals a. So these are our two kind of special cases. One that just kind of can still be called slope-intercept form, but just looks a little funky. And an analogous case that really kind of breaks slope-intercept form, but hopefully by analogy to the one that's easier to understand, we can understand this one pretty readily. I'm trying not to cough in your ears, trying not to cough into the microphone. Okay, so moving on to the next topic in this section, parallel and perpendicular lines. So the idea of parallel lines is geometrically, this is what would happen if you took a line. That was a pretty bad attempt at drawing a straight line. If you took a line and you picked that line up and translated it, if you moved that whole line left or right or up or down, but kind of kept the didn't rotate it at all, kept the direction the same. That's the idea of a parallel line. You could either think of the line being translated left or right or up or down or some combination of those, but the important thing is we didn't rotate it. It doesn't have a different angle. It still points in the same direction. So these are parallel lines. So kind of geometrically, that's how we might think of what a parallel line is. It's a translation along the X or Y or both directions of a line. So algebraically, how can we think of that? In other words, in terms of things like slopes and intercepts, what does this mean? Well, parallel lines have the same slope, but usually different intercepts. Right? The slope is the same between the two lines because we didn't change their directions or their angles. So if I go to the right 1 unit, I still go up m units. But their y-intercepts do change. So that's the idea of parallel lines. Same slope and usually different intercepts. If we had the same slope and the same intercept, we see that the slope-intercept form defines a line in terms of its slope and its intercept. If we had the same slope and the same intercept, we would have exactly the same line, just the same line twice. And I don't know, do we want to call those, if I have the same line twice, do I want to say that those are parallel lines or not? I suppose we could allow for the same intercepts and call a line parallel to itself. I don't think there's anything wrong with that, but at least typically we think of these as having different intercepts. There are some special cases where maybe we can think of them as having the same intercept, and that maybe has some implications for things like number of solutions for a linear equation. If I had two lines that had the same slope and different intercepts, that might be kind of related to the idea of an identity instead of a conditional statement, something like that. But typically when we're thinking of parallel lines, we're thinking of same slope but different intercepts. So they look like this. So what about perpendicular lines? If I have a given line and I want to find a line perpendicular to it, well, first I need to say where on this line my perpendicular line lies. Maybe it goes through this point. And a perpendicular line is one that meets with a right angle. And it turns out that, let's say that the blue line has slope a over b. B could be 1, so this could be a slope of 3, and we just write 3 over 1. Then the green line will have a slope of negative. We can see that, like, for instance, the blue line has a positive slope, so the green line has to have a negative slope. And if the blue line is pretty steep, the green line will be pretty shallow. And if the blue line is pretty shallow, the green will be pretty steep. So we invert the fraction. So if my blue line had a slope of, like, you know, say 5 halves, 5 over 2, a pretty steep line, my green line would have a slope that looks like 2/5, a pretty shallow line. And the sign would be opposite. So I changed the sign and flipped the fraction. So perpendicular lines, these are lines where, say, M1 equals -1 over M2, where the slopes are related this way. We flip the fraction and then pick up a negative sign. Okay, so let's come down to these 3 examples and take a look at 3 collections of 2 lines. For instance, 5x minus 2y equals 11, 5x minus y equals 7. And for each of these, we'll try to determine whether the pair of lines is parallel, perpendicular, or neither. So we saw really the important characterization here is the slope, or parallel if we have the same slope, perpendicular if the slope follows this specific formula. And now if I just pick kind of 2 random slopes, chances are really good that they're not going to be the same 2 numbers and they're not going to follow this very specific format. There's lots of lines that are just not parallel and not perpendicular to one another. Okay, so I want to find the slope easily. I suppose I could pick 2 points on each of these 2 lines, from each of those find the slope and go that route, but I also could just put this into slope-intercept form. I could solve for y. Adding the 2y to the other side, I get 2y equals 5x minus 11, and then I divide by 2. And I see that the slope of this first line is 5 halves. I think it is good practice to always actually put it in slope-intercept form and not try to, use whatever you were given up here to try to figure out what the slope is. There are lots of other formats well, several other formats that the equation can be written in. And I think, just forcing it into the mold y equals mx plus b is the best way to go, instead of trying to, figure out a rule that when it's written this way, then this is what the slope is. It's easy to get, especially maybe off by a negative or get a fraction flipped or something like that. And then for my second equation, I can add y to both sides, subtract 7. So I get y equals 5x minus 7. And I see my second slope is 5. Are these parallel? Is it true that m1 equals m2? No, that's not true. 5 halves not equal to 5. Not parallel. Is it true that m1 equals -1 over m2? Is like 5 halves -1/5? No, that's not true. These are not perpendicular either. To the these two lines are neither parallel nor perpendicular. Now, if I look at something like x equals -3, that line, versus x equals 2, that second line, this can be a little bit tricky, right? If my strategy is just force it into the mode of slope-intercept form, just solve for y in terms of everything else, but there are no y's explicitly here. So if I have x equals -3, I know that this is a vertical line. My points in the two-dimensional plane that follow this restriction, I can pick y any way that I want. I can pick it to be 0 or +10 or -3 or whatever. As long as x is -3, as long as that first coordinate is -3, then it satisfies this condition. X equals 2 has a similar story. Y can be chosen however we want, as long as the first coordinate is 2, uh, then we satisfy this condition. And I do see that really one of these lines is just a horizontal translation of the other. These are actually parallel lines. So, oh, went a little too far. Parallel lines have the same slope, and maybe we want to append this special case or both vertical lines. We probably don't want to say that two undefined slopes are the same slope. It's usually not a good idea to say the things like, you know, two undefined quantities are equal to one another, or two infinite quantities are equal to one another. Things like that, you can kind of get into a little bit of trouble. So we'll just address this special case as a little addendum. Parallel lines either have the same slope, if that slope is a real number, or are both vertical lines, in which case the slope is undefined. And then let's look at these two. Now, again, we have pretty nice, kind of general forms of linear equations here. So we can solve these for y in terms of x in constant terms, get everything in slope-intercept form, find our two slopes, and then look at their relations. So a little more straightforward for part C rather than part B, where we had to really think back to the geometric meaning of parallel lines and so on. So let's start with the first one. Let's solve for y. So we add 2y and subtract 7. And then we divide by 2. So my first slope I see is 4. For my second, I want to solve for y in terms of the other. So maybe I subtract 3x. And then I divide by 12. And 9/12 will be 3/4 when I divide out the factor of 3. And maybe I'll call this M2 and maybe this M1. M2 is -1/4. So is it true that M1 equals M2? Is it true that these are parallel lines? Well, no, these are not parallel. Is it true that M1 is -1/M2? Or vice versa. I can think of this is equivalent to M2 being -1/M1. Right, I could just multiply by M2, divide by M1 to move back and forth between them. And yeah, I actually see that M2 is indeed -1/4, -1/M1. So these are perpendicular. Any questions so far? Okay, and then one last little example here. We have a cost of a dinner banquet that's modeled as C equals 750 plus 42G, where G is the number of guests in attendance and C is the total cost. We like to graph this relationship between guests and costs and interpret the slope and intercept in the context. Well, since G represents number of guests, I'm gonna choose to graph this only for positive or non-negative G's. I see that I have a slope, M equals 42, and I have a y-intercept, or maybe I should call it a c-intercept, I suppose, but we'll just call it a y-intercept, 0, 750. So when G is 0, we're up here at 750. That's 1 point on our line. And then we know our slope is 42. So if I go over 1 unit, I go up 42. If I go over, let's say 10 units, I go up 420. So what's 750 and 420? 1170. And that's my line. So in this context, what might these two things mean? Well, slope for each additional guest, if G goes to G plus 1, if I add one more guest, then cost is increased by $42 or 42, whatever. If I add two additional guests, cost is increased by 2 times 42, $84. So my slope, 42, is probably cost per guest. And then if I have 0 guests, I have to pay 750, right? 750 is kind of the base charge, maybe like the rental fee for the room. Or like the flat fee. So we pay basically 750 to rent the room and then $42 per guest for each guest in attendance. So that might be an interpretation. Now, I mean, is it guaranteed that that's exactly what this means? Maybe not necessarily, but I think that would be a pretty reasonable interpretation in this context. Any questions on anything from slope of a line? Okay, so moving on to 3.3 then, finding the equation of a line. So just kind of recalling from the last section, if we wanted to find an equation of the line with slope 3/4 and y-intercept 0, -5, that's pretty much the same problem we just did, right? Before we had an equation in slope-intercept form, and we found the slope and the intercept from that equation, but we could have gone the other way just as easily. Here I'm given slope and given intercept. This would be b is -5. And if I want to find an equation for a line with this slope and this y-intercept, I just plug that slope and intercept in, right? I can go either way with the slope intercept form. I can look at the form and determine the slope and intercept pretty quickly. Or I can, if I'm given a slope and intercept, generate an equation of a line. Okay, let's look at this graph. Let me zoom in just a little bit, a little easier to see on your screen. So here I have a graph of a line, and we want to find an equation of the line. So I do see that I have an intercept here, it looks like at 0, -1. Anytime we're given a graph like this, we're going to assume that if it looks like the line goes through an integer point, it does. We see another integer point that's actually labeled here, maybe another one down here, maybe another one up here, for instance. But I do see that I have a y-intercept of what? 0, -1. So this tells me that my b in my slope-intercept equation is -1. And then what's my slope? I could use 2 points and find my slope, but I could also use a more kind of geometric definition. I see that to get from this point to this one, I need to go over 2 and down 3. So what's my rise over my run? -3/2. So going to the right 2 units means that I go down 3 units. So a rise of -3 over a run of 2. That's my slope. Now I have a y-intercept and a slope. My equation is y equals -3/2 x plus b, or -1. So again, we can use slope-intercept form in both directions. We can use the equation to figure out what the slope and intercept are, or given a slope and intercept, we can generate an equation. Now, one other form that is often useful is the so-called point slope form. And where this is typically useful is if we're given a slope and we're given a point that the line passes through, but maybe that point is not the y-intercept. Right up here, we're given a point and a slope, but the point has to be the y-intercept for me to be able to get b right off of that point and plug it into the slope-intercept form. If I'm given a point instead of, say, the y-intercept, if this was not a messy point, but I'm given this point instead, what is it, -4, 5, I can't look at this and just figure out what b is on the basis of a point that's not the y-intercept. So if I'm in that situation, if I'm given a slope and some other point that's not the y-intercept that the line passes through, it might be better for me to use point slope form. Where does point slope form come from? Well, suppose I have 2 points, kind of an arbitrary point x, y, and a given point x1, y1. Let me make those ones a little bigger so they don't just look like commas. Then what's the formula for slope? It's the rise, say y minus y1 over the run x minus x1. Let me just multiply by x minus x1 on both sides. That's all the point slope form is. It's just rearranging the formula for slope, just putting that x minus x1 on the right side multiplied by m instead of being underneath the y's. So if you forget, what point slope form is, or you're getting confused with what goes where, that's really all that it is. It's just a rewriting of the slope formula like this. So if I knew 2 points and wanted to find the slope, I would use this formula. If I know the slope in 1 point and want to find the equation of the line, I use the point slope form. So let's try to find an equation of the line with slope -2. So this is m passing through the point 3, 1. This is what we're calling x1 comma y1. And at this point, I just plug in. I have y minus y1 is 1 equals m negative 2 times x minus x1. X minus, and x1 is 3. Now, one thing that's a little easy to get mixed up on in point slope form is you might be tempted to try to find something to plug in for x and y. But remember, the goal here is to find an equation of the line. So we want to end up with an x and a y in the answer. So I'm not looking for some other piece of information to plug in for x and y. I want to have x and y in the answer. But I want to get rid of, or I want to plug in for the y1, the x1, and the m. Those are the ones that I want to use my information to say what they are. But this x and y here, these are what we want to end up with. And I might clean this up a little bit. I could leave it this way. This isn't wrong. But I might say, y equals negative 2x distributing. I would have plus 6 plus 1 plus 7. So I could write it this way, or I could write it this way, either in point slope form or slope intercept form, or even in the general form, 2x plus y equals 7. We can go back and forth between all of these different forms. Okay, what about this one? Find an equation of the horizontal line passing through the point negative 2 comma 5. So again, let me just copy this down here. So again, my goal is to figure out what is x1 and y1, and then what is m. I'm given a point here, so I'll call this x1 comma y1. So I have y minus 5 equals something times x minus a negative 2 is x plus 2. But here I have a horizontal line. Well, a horizontal line, that's one where m equals 0, right? As I move left or right, I don't go up or down at all. So this is y minus 5 equals 0 times x plus 2, or just y minus 5 equals 0, or simply y equals 5. Right? A horizontal line is one where I can change the x component freely, but the y component has to remain fixed. So I can have anything comma 5, that's a point on the horizontal line. And that meshes with what I got out of the point slope form. Okay, now what about an equation of the vertical line passing through the point 5 comma negative 4? So here I have 5 comma negative 4 and vertical line passing through here. Now again, for the point slope form, I need x1, y1, but then I need m. But m is undefined, right? So I'm not really sure what to do here. Right, as far as the point slope form, I can't just like plug in the word undefined or something and get something meaningful. So I have to think a little bit deeper about this, and I say, okay, well, really my set of solutions, it's really any point where the first coordinate is 5, where x equals 5. If y is 10 or negative 10 or 0, those are all points on the vertical line passing through x equals 5, y equals -4. So my criterion is simply x equals 5. Again, this kind of vertical line, it kind of breaks the point slope form a little bit too, because it doesn't really have a nice value for m for me to plug in. So I have to think a little bit more deeply. I have to recognize this is a special case and maybe ask a little bit more broadly the question, what do I mean when I have an equation of a line? I'm representing a constraint on the points that I'm considering valid. And what ought that constraint be here? That the x coordinate always has to be the number 5 and the y coordinate can vary freely. Any questions?
It wouldn't
Yeah.
it wouldn't be -5.
Well, we're going through the point x equals +5 and y equals -4. So we're going through this point.
But it say x minus x1. So wouldn't it be -5?
Yeah, but that's if we were to use point slope form, right? But the problem with point slope form is we don't really have an
Point
m
slope.
to plug in. So point slope form for this problem is kind of out of the window. We could, if we wanted to think a little bit more abstractly, this is going maybe a bit outside of the material for the course, but we could kind of look at this and say, well, a vertical line from the perspective where x is the horizontal axis and y is the vertical axis, that's kind of a horizontal line from the perspective where if I flip things over where y was the horizontal axis and x the vertical. There's nothing super special about picking x to be the horizontal axis and y the vertical. There's no reason we couldn't have labeled them differently. And then we could think of having something like x minus x1 equals, we'll call it like m tilde, y minus y1, as maybe like an alternative point slope form for this different, mirror world where we kind of have labeled all of our x's and y's differently. In this like mirror world, the vertical line becomes a horizontal line. So the slope, this kind of mirror slope, is 0. And then I do have something like x minus 5 equals 0, but notice that x minus 5 equals 0. So now when I solve for x, I get x equals 5. So I do get consistency, but I have to really expand my thinking. And, that's something that's kind of beyond the scope of this course, but that's a really interesting point though, to bring up. In this course, we want to stick pretty rigidly to the x-axis being horizontal and the y-axis being vertical. But as we, mature in mathematics and see future courses and so on, there's no particular reason that x should always be the horizontal axis and y always the vertical axis. So we could expand our thinking a little bit, generalize a little bit, and come up with kind of a mirror version of the point slope form, and we could see that something similar yields the same result. But yeah, very good question though. Okay, any questions from anything today? All right, I will stop the recording then.